Grab your socks and hold on to your hats. We're going to discuss which functions are integrable. So the goal of this admittedly kind of long recording is going to be to discuss which functions actually can be integrated, which functions are integrable. Everything we've done so far, a lot of the theorems have started off with like, oh, assume a function is integrable and then prove some stuff. And we've really held off on trying to show which functions actually are integrable. What we're going to need is something that I refer to as the close partition criterion. Okay, so if we have a function defined on an interval, it's said to satisfy the close partition criterion, which I abbreviate as CPC, if for any epsilon there is a partition whose upper and lower sums only differ by less than epsilon. So for any epsilon, we can find a partition so that the upper and lower sums are extremely close in value. What would this look like? So if I draw from an interval a to b, okay, let's draw a function that has some relatively flat parts, but also some very steep parts. Okay, so here's my function f of x. Let's say I want epsilon to be fairly small. Okay, so I want the upper and lower sums to be very close to one another. Now, if I take a partition, which is pretty coarse, like this, then my upper sum would be something like this. So on each interval, I'm just looking for the supremum, and then I'm making rectangles of that height across intervals of this width. Okay, so here's the upper sum associated to the partition I drew in green. Now in blue, I go ahead and use the infimum for lower sums, and observe that the difference between the upper sum minus the lower sum is going to be all of this area, this little bit, all of this, and all of that. Okay, so this partition does not satisfy the property that the upper and lower sums are especially close to one another. But if I change the partition, so now instead of using the partition that I initially put down here, what we're going to do is we're going to change the partition by making it much, much finer. Okay, now if I change the partition to be much, much finer, so now it has way more points in it. The norm of the partition is now much smaller. Now on each interval, okay, the sup minus the inf is still going to give me a difference. There's still an area that's accumulating of sup minus inf over each piece of the partition, but you can kind of see that it's going to be a much smaller amount, even by the time I go all the way across. Since I made the norm of the partition so small, even where the function is moving very steeply, sup minus inf might be pretty big, but because the norm of the partition is so small, that's still a fairly small rectangle in terms of area. Okay, the difference between the sup and the inf times the interval length, in other words, what is going to be part of the upper sum minus the lower sum, is not a very big amount. Okay, so compared to the notion of Darboux integrability, what is worth pointing out is that for the close partition criterion, we're using the same partition. The upper sum minus the lower sum of the same partition needs to be small. For Darboux integrability, we needed something like, if delta is sufficiently small, if the partitions are sufficiently fine, and I take two different partitions, then the upper and lower sums, the upper sum of the first partition and the lower sum of the second, are close to each other. So this is way easier to satisfy. Darboux integrability requires for sufficiently fine partitions, upper sums and lower sums are close to each other in value, even for different partitions. Here we want the upper sum and the lower sum to be close to each other, but it's for the same partition. So this is a weaker condition than Darboux integrability. It's easier to satisfy. Right, which doesn't mean it's the same thing, okay? So it's a convenient definition because we use the same partition for both upper and lower sums, but it's definitely not the same thing as Darboux integrable. Or is it? Theorem: a function is integrable if and only if it satisfies the close partition criterion. Okay, so this is really the goal. We want to show that this easier condition, the closed partition criterion, is actually equivalent to Darboux integrability. And we already know Darboux integrability is equivalent to Riemann integrability. But we do in fact have to prove it. That is a good point. Okay, let's prove one direction first. If a function is Darboux integrable, then it satisfies the closed partition criterion. So Darboux integrability says for any epsilon, okay, u of delta minus L of delta will be within epsilon of each other, meaning for any partitions whose diameter, whose norm is less than delta, we have that the upper sum of one minus the lower sum of the other is less than epsilon. Okay, the distance between an upper sum and a lower sum of two different partitions, as long as they both have norm less than delta, will be within epsilon. This comes from assuming the function is Darboux integrable. And yes, it's because they can both be forced to be epsilon over 2 away from the value of the integral. From Darboux integrability, for sufficiently fine partitions, all upper sums and all lower sums can be any distance we want from the value of the integral. So if I force them both to be within epsilon over 2 of the value of the integral, then by the triangle inequality, they are within epsilon of each other. So this is true for any two partitions whose norm is less than delta. So if I just pick the same partition for both of these, then we have satisfied the closed partition criterion. Upper sum minus lower sum of the same partition, if I choose them to be the same, will be less than epsilon. This direction of the proof, pretty straightforward. Yeah, so Darboux integrability is very general. Okay, for any partitions of given norm, you get some stuff. Closed partition criterion is there exists at least one partition with that similar property. So if I have something in general, it's easy to show that it works for a specific choice, but the reverse will in fact be harder. So let's start it. If we assume the closed partition criterion, that says for any epsilon there is some partition whose upper and lower sums are within epsilon of one another. What we need to show, however, for integrability is that any two partitions of sufficiently small norm have upper and lower sums close to the same value. So we're going to do this in several steps. The first one is, if f satisfies the closed partition criterion, it must be bounded. We know, for example, that if a function is integrable, it must be bounded. And if we're trying to show closed partition criterion implies integrable, it's a useful step to show, I don't know yet whether or not the function is integral, but at least it's bounded. So try to do this. Pause now, work this out. Assume the closed partition criterion, prove the function is bounded. Okay, hopefully you were in fact able to prove that. It's best done, I think, as a proof by contradiction. If you assume a function is unbounded, maybe it's unbounded above. Any partition will be unbounded above on one segment, and then you're going to get upper and lower sums whose difference is infinity, not less than epsilon. So let's continue our proof. Okay, so if I assume closed partition criterion, I now know that the function must be bounded, so we can let m and capital M be the inf and sup of the function as we traditionally do. So now what we're going to do, we're going to utilize the closed partition criterion to construct a sequence of partitions. So assuming closed partition criterion, we know for any epsilon, there is a partition, so the difference between the upper and lower sums is less than epsilon. So if I pick epsilon equals 1, there is a partition, I'll call it p sub 1, so that the upper sum minus the lower sum is less than 1. And now we just sort of work inductively. I can always pick a partition p sub n plus 1 so that the upper sum minus the lower sum is less than 1 over n plus 1. But I also want to be more specific. Not only is pn plus 1 a partition so that this difference is small, it's also a refinement of the partition before it. Because remember, if I pick a partition whose upper and lower sums are very close, and then I refine it, I only make the upper and lower sums closer to each other. So start off with a partition so that this difference is 1. Then by closed partition criterion, I can find something so this difference is less than a half. Take that something and refine it with the one you already had, and you still have something so that the difference of upper and lower sums is less than a half, but it's also a refinement of the one that came before it. Then get a partition so that the difference is less than a third, and refine it with the one you just got, p sub 2. Make that p sub 3, and so forth. So, having already constructed one partition, let p prime be a partition so this difference is less than 1 over n plus 1, and then refine it with the one you had, and that's your next partition. So every partition doesn't just accomplish that the upper and lower sums are close to one another. Each partition is a refinement of the one that came before it. So, since the partitions are refinements of one another, the lower sums must be monotone increasing, and the upper sums must be monotone decreasing, but the lower sum of a particular partition is always less than or equal to the upper sum of that particular partition, giving us this infinite chain of inequalities. Upper sums decreasing, lower sums increasing. For a particular index, the lower sum is less than or equal to the upper sum. So while this is monotone increasing, it can never get any larger than a single one of these, which are monotone decreasing. Right, and we did prove a bunch of results about refinements of partitions regarding upper and lower sums, and now we're starting to use that. So we have this chain of inequalities. Lower sums are increasing, upper sums are decreasing, and they do bound each other. But we also know that for a particular choice, the upper sum minus the lower sum is less than 1 over n, because we were using the closed partition criterion. So the sequence of upper sums is decreasing and bounded below. It's decreasing because these are refinements of one another. They're bounded below because all of the upper sums have to be bigger than or equal to each of the respective lower sums, which are all bigger than or equal to this first lower sum. So the upper sums have a limit. Similarly, the lower sums have a limit. But the difference between the upper and lower sums is less than 1 over n. So since this sequence has a limit and this sequence have a limit, but the distance between them is going to 0, they have the same limit. And we are definitely using that the partitions are refinements of one another. The fact that the partitions are refinements as we go along gave us the monotonicity of this sequence. And this one, of course. So not only are they close to one another, but they bound each other, right? That's where the refinement came in. So let's let this shared limit just be L. Our goal, of course, is to show that the function must be integrable and the value of the integral is L, but we're not there yet. We just know that we have made a particular sequence of partitions whose lower sums and upper sums have the same limit. We now need to show that for sufficiently fine partitions, even if they're not drawn from this sequence, the upper sums and lower sums are arbitrarily close to L, and that's a big task. Right, we've just made a shared limit for some partitions. Now we need to start working on any partition of sufficiently small diameter. Okay. So we made a very specific sequence. It's a sequence of partitions whose upper and lower sums have the same limit, which is not quite the same thing as showing that for any partition whose diameter is less than delta, this this function of infima of all lower sums and this function of suprema of all upper sums share the same limit. This would be Darboux integrability. This is what we're working towards. And we're going to do it following a plan. First, let epsilon be positive. Then we're going to pick an appropriate delta and a partition of norm less than delta. We have to pick delta appropriately, of course, and we'll see how to do it. Then what we want to show is that the lower sums and the upper sums are within epsilon of L, the L that we found earlier, which was the shared limit of the sequence of a specific sequence of partitions in the sequence of upper sums and lower sums. Therefore, okay, since this was any partition of norm delta, and the lower sum was bigger than L minus epsilon, and the upper sum was less than L plus epsilon, if this is true for an arbitrary partition of norm delta, all of the upper sums are less than or equal to L plus epsilon, then the supremum of all possible upper sums is less than or equal to L plus epsilon. And if I can show for an arbitrary partition of sufficiently small norm that the lower sum is at least L minus epsilon, then the infima of all lower sums of partitions whose norm is less than delta will be at least L minus epsilon, and we'll get this. And if epsilon was arbitrary, and L of delta and U of delta are trapped within epsilon of L, then in fact L of delta and U of delta have the same limit, it must be L, and by Darboux integrability we have that the value of the integral is L. So this is our plan. Of course we have to figure out how delta can be chosen to guarantee both of these things. Once I can guarantee both of these, however, this chain of argument falls in. So the real goal is to pick delta so that we can establish step 2. Once we have step 2, that will imply step 3 and step 4 pretty quickly. Okay. All right, so let epsilon be positive, and we want to pick a partition whose norm is less than delta, which we will pick later. Okay. Our goal is to show that the upper sum must be less than or equal to L plus epsilon over 2, where L is specifically that shared limit of the sequence of upper and lower sums for a specific sequence of partitions that we got using the closed partition criterion. So the upper sums were a decreasing sequence with limit L. Since the upper sums are decreasing towards L, I can pick an index so that past that point, the upper sums are within epsilon of L. And they can't be below L because they were decreasing towards L. So past a certain n, all the upper sums are within epsilon of L. Now fix this single partition. This was a partition from our sequence that we got with the closed partition criterion. This lower index n is not going to change from this point forward, okay? I picked a specific partition from that sequence to get this inequality here, and now I am locking down this partition. It's not going to change. Let capital N be the number of points in that partition. I have no reason to suspect it's related to lowercase n. Okay? It's probably much larger. So capital N is the number of points in the partition, so I start at index 0. I'm going to end at index capital N minus 1. Right, so we got to be pretty careful about what's what here. P is one specific partition we picked, okay? P sub n is now from our original sequence of partitions given by the closed partition criterion. Okay, so P is our arbitrary partition with norm delta. We're going to later on fix what this delta was. P sub n is a specific partition which has capital N points in it. What I do is I refine the arbitrary partition we picked along with the specific partition from that sequence. So whatever P was, our arbitrary partition, I've refined it with something, and remember this is not going to change from this point forward, so it has exactly n points, capital N points. I refine the two partitions. How many points did I add in? At most capital N. If you wanted to be really picky, you could say at most capital N minus 2, since the endpoints had to be in both partitions. But I'm not going to stress on that, okay? This has capital N points, so by refining them, I add at most capital N points by doing this refinement. Okay? So from our arbitrary partition, I've now refined it by adding at most capital N points. Therefore, every time I add a single point, the value of the upper and lower sums can change by at most this difference times the norm of the partition. So since I added capital N points, when I refine the partitions to get P prime, the upper sum could only go down, but by no more than the number of points I added times the amount that a single point can possibly throw off an upper sum. I also know that P prime is a refinement of Pn, so I get this. Also, Pn was chosen so that the upper sum was within distance epsilon over 2 of L. So Pn was chosen to be within epsilon over 2 of L. P prime is a refinement of Pn. And P prime has at most capital N points different than P, so its upper sum could only be off by this much. So here is our chain of inequalities that we now have. This is an upper sum for our arbitrary partition P. All of this one was our refinement of P with Pn, and this is Pn, and this is all very specifically in the correct spot. So therefore, since the upper sum of f with respect to P minus this quantity is less than or equal to L plus epsilon over 2, we get that the upper sum of Fp is less than or equal to L plus epsilon over 2 plus all of this stuff. Okay, so what's going on here? we have our interval from A to B, and we have our function. So from the closed partition criterion, we get a specific, and we had epsilon was an arbitrary number that was given to us. We get a specific Pn, so that the upper sum is within epsilon over 2 of L. Remember, the upper sums on this specific sequence were decreasing towards L, so I know that this is bigger than or equal to L, and now I'm picking n large enough to make it within epsilon over 2. So I'll put that in red. Okay, I don't want to make it too fine because the picture is just going to get ugly. Then I pick an arbitrary partition, P, whose diameter is extremely small. You should think of this as being way, way smaller, so it has a whole lot of points in it. I'm not going to make it too many, but in your mind, like, this is just ridiculously more, and it doesn't go past B, of course. Then what I do is I make a refinement, P prime, by refining the two partitions. So I just take all the points from both partitions that are now in play. And this is what we're going to work with. So since this is a refinement of P, the upper sum could have only gotten smaller, but it was refined by adding, at most, the number of points that were in this specific partition, which is not going to change as I keep working. So I added in a few points. So while this upper sum is less than this one, it's not off by more than the number of points in this partition times the distance between the sup and inf of the function on this interval. So if I pick delta to be less than this, notice capital N, the number of points in the partition P sub lowercase n, we were very specific to say P lowercase n is not going to change. So lowercase n, P sub lowercase n is a fixed partition, and capital N is the fixed quantity of points in that partition. So capital N never depended on delta, okay? So I can use capital N in the definition of delta. Capital N, the number of points in that partition, did depend on epsilon, because epsilon was picked at the beginning, and then I picked a partition from the closed partition criterion that satisfied some stuff regarding epsilon, but that's fine. N is allowed to depend on epsilon, and then I can use both of them to define delta. So if I pick delta to be less than this, then the upper sum of FP was less than L plus epsilon over 2, plus delta times capital N minus lowercase m, which exactly cancels that and gives us an epsilon over 2. So the upper sum of FP is no larger than L plus epsilon. The upper sum of this arbitrary partition, whose diameter is at least this small, is very close to the refinement P prime, which was not too far off from the sequence, the partition P sub n, which was from the sequence of closed partition criterion generated partitions. And we've achieved that the upper sum of F with respect to this arbitrary partition, whose diameter is less than this specific delta, is within epsilon of L. And this does merit repetition. Okay, we are actually allowed to pick delta after capital N has been fixed. Okay, N was the number of points in a specific partition. And the partition had norm less than delta is an easy mistake to make. That's not quite true. P sub n was from our sequence from the closed partition criterion. Right. The sequence that was generated by the closed partition criterion, all we needed was that the upper and lower sums were close to each other. The norm or diameter of those partitions never came into play. The closed partition criterion actually has nothing to do with diameter of partitions. Okay, so this P sub n only had to do with epsilon. So we can in fact conclude for an arbitrary partition whose norm or diameter is less than this particular delta, the upper sum must be less than L plus epsilon. You can similarly conclude that the lower sums are at least L minus epsilon. So since U of delta is less than or equal to L plus epsilon and epsilon is arbitrary, U of delta must converge to L. Okay, a very similar argument gives me that L of delta must converge to L. And therefore, we get Darboux integrability from the closed partition criterion. Darboux integrability required us to work with any partition whose norm was sufficiently small. The closed partition criterion, however, just says find a partition whose upper and lower sums are close to one another. Okay, so work through this, finish up the details, but the hard work has already been done. Okay, so think back to that bullet point 1, 2, 3, 4. Okay, this is really just wrapping up parts 3 and 4. Part 2 we already took care of, and therefore we're good. Just sort of repeat the argument for part 2 to get the stuff about lower sums. So why does the closed partition criterion really help us? Okay. Suppose f is integrable on a big interval from a to c, and I pick a point in between. We already know if both of these integrals exist, we can glue them together to get the big one. But now we can actually say, if the integral on the big interval exists, we can also split it apart and get integrals on each piece, and then this equation will also be satisfied. So to prove it, let epsilon be positive. Since f is integrable, I'm going to use the closed partition criterion. I know that this is equivalent to integrability. So I can find a specific partition whose upper and lower sums are within epsilon of each other. And yeah, we already showed we can glue together two small pieces if I know these are integrable. But now we're just doing it in reverse. That's exactly right. So I pick a specific partition whose upper and lower sums are within epsilon of one another. I might have to refine it by adding a single point b. Okay, that now gives me two partitions, the left bit and the right bit. If I add a single point, I now have a partition from A to B and also a partition from B to C. But adding a single point to the partition only made the upper sum smaller and the lower sum bigger. It pushed them closer together. So since these were within epsilon of each other, so are these. Okay. So since I was able to find a partition on the left, whose upper and lower sums are within epsilon of each other, then the function satisfies the closed partition criterion on the left bit. Okay, and similarly on the right. So where did this inequality come from? So the partition on the left bit, I get actual gaps here between upper and lower sums, and I accumulate them up to the endpoint B. That's definitely smaller than if I went all the way. Okay, so here's a picture to illustrate this point. We've got A, C, B. Here's my function. We know the function is integrable from A to C. So I let epsilon be positive and I pick a specific partition so that the distance between sup and inf over each of these intervals is less than epsilon. So when I do this sup minus inf and I get all these boxes, oh sorry, I didn't put b in this interval. That was on purpose. So I get one sup minus inf there. Here's a sup minus inf. Here's a sup minus inf. And a sup minus inf. The sum of the red area is less than epsilon. That's our closed partition criterion. For any epsilon, there is a partition so that if I split it up according to this partition and I do sup minus inf over each of those intervals, the total area accumulated is less than epsilon. So now what I do is I refine this partition by adding b, and I only do the same process up to b. And then I just stop. Now what I have is I have a partition from A to B, and the total I accumulated is less than what I started with, which was already less than epsilon. I was able to make a partition from A to B, so that doing sup minus inf along the way gave me a total of definitely less than epsilon, because this accumulation is definitely less than all of this, which was less than epsilon, because the original function all the way from A to C satisfies the closed partition criterion. And of course, you can do the same thing on the right as well. And yeah, this is way easier to talk about and to work with because you get to pick a specific partition that can have some very large intervals. Okay, if the function is nearly constant on a big chunk, in other words, the sup and inf are not very far off, you can go ahead and use a single large piece in a partition. The norm of the partition will now be quite large, but the closed partition criterion doesn't care about diameter of partition, it only cares about the distance between the upper and the lower sums. So we get a general additive identity here. We're now going to define, okay? If a and b are two real numbers, if I want to integrate from b to a, it's just the opposite of integrating from a to b. This is just by definition, we're declaring this to be true. So now this always works. If I want to integrate from a to b, I can go from a to b and then b to c. That's overall integrating from a to c. As long as all three of these integrals exist, it doesn't matter anymore which one is bigger than which. I don't necessarily need the interval to go from a to b. Okay, if b is actually to the left of a, this is just negative, and so is this, and then so is this. Okay. So now let's finally get to addressing the question, which functions can be integrated? Here's a big theorem. If a function is monotone, then it is integrable. And this will, in fact, vastly expand our library of integrable functions. If you think about it for 5 seconds, it doesn't seem that way, because we don't know a whole lot of functions that are monotone overall, but we'll see why this is actually a big step. So suppose f is monotone increasing. For a decreasing function, it's going to be more or less the same thing. So since the function is monotone increasing, supremums are always achieved at right endpoints and infimums are always achieved at left endpoints. So now let P be any partition whose norm is less than some fixed epsilon over this quantity, f of the right endpoint minus f of the left endpoint. Observe, this is your overall supremum, this is your overall infimum. Okay, so what's happening here? We have a function that goes from a to b, and it's monotone, and it's, say, monotone increasing. It doesn't have to be continuous. It doesn't have to be strictly monotone either. But, there it is. On any interval I pick, because the function is monotone increasing, the supremum's always at the right endpoint and the infimum's always at the left. So I'm just picking a specific partition, and now I'm going to compute upper and lower sums. But the upper sums and lower sums would normally be a little inconvenient for an arbitrary function because you don't know where sups and infs happen. But for a monotone function we do, sups and infs are always at endpoints of the intervals. So we're going to show that the closed partition criterion is satisfied. So pick epsilon to be totally arbitrary, and then I'm going to pick any partition whose norm is less than this quantity. So the upper sum minus the lower sum is given by here, where these are the sups and infs on each interval. However, the delta xi's are all less than or equal to delta, the norm of the partition. Okay, so term by term, I say this is less than or equal to, replacing this with a delta, and factor out that constant. Now the sups are always the right endpoints, and the infs are always the left endpoints. So that's what's happening here. This is just a straight up equality. Because the function is monotone increasing, the sup is at the right endpoint and the inf is at the left endpoint, and delta was chosen to be less than this quantity right here. So now I have upper sum minus lower sum is less than all of this. But now let's take a look at this sum. This is now a telescoping sum. As my index goes from 1 to n, I get f of x1 minus f of x naught, f of x2 minus f of x1, and those f of x1s will cancel. In fact, all that remains is the last f minus the first one. But we had a partition, so the last xn and the first one must be very specific values. This has to be f of b, this has to be f of a. The last point in the partition is the right endpoint b, the first point is the left endpoint a. This cancels that, and you get epsilon. So for any monotone increasing function, we were able to exploit that the sup and inf are right and left endpoints to get a telescoping sum here, and that simplified our lives greatly. And we've now shown that the closed partition criterion is satisfied. For an arbitrary epsilon, we found a partition whose upper and lower sums are less than epsilon apart. It's integrable. Next up, suppose a function is continuous on a compact interval, then it's integrable. And this will also expand our library a lot. Okay, not only are monotone functions integrable, but so are continuous ones. Okay, since f is continuous, it's uniformly continuous. So for an arbitrary epsilon, there must exist some delta. This is now using uniform continuity, so that for any 2 points, if they're within delta of each other, then their values under f must be within a specific value, and I'm going to use epsilon over b minus a, where b minus a is the length of the interval. So let P be a partition whose norm is smaller than this delta. Okay, so now what's happening? We have from A to B, I have a continuous function. If I pick epsilon to be, say, this distance up in the range, what we get to do is by uniform continuity, as I move along, there must be a delta so that any 2 points within delta down here will produce values within epsilon up there. Okay, so maybe delta is pretty small, but it still exists. Any 2 points whose distance is less than delta, down in the domain, the distance in the range will be less than this epsilon here. I'm picking a norm, I'm going to pick a norm given by this delta. So now pick a partition whose norm is that small, which means that on each piece, some nice stuff is going to happen. So on any piece of this partition, f is continuous and therefore has a max and a min. The max has to happen somewhere in the interval, and the min has to happen somewhere in the interval. But because they're from the same piece of the partition, they're the max and the min on one of these intervals, they are within delta of one another because the partition had norm less than delta. So any 2 points in this interval are within delta distance of each other. So now I'm going to use uniform continuity. The distance between the max and the min must be less than this. What I did is I picked delta according to uniform continuity so that any 2 points within delta of each other, the value within the range will be within a fixed positive amount, and we picked epsilon over b minus a. So on each piece of the partition, the sup and the inf are actually maxes and mins because we're a continuous function, and the distance between the max and the min is now quite small. By picking a very, very fine partition, for a continuous function, the max minus the min is not all that large. So now I'm going to take this partition and compare the upper and the lower sums. By definition, upper sum minus lower sum, I just get sup minus inf, but those are actually max minus min. And we've already established that the max minus the min is always less than epsilon over b minus a. So term by term, this parenthetical term can be replaced with epsilon over b minus a and then factor out that constant. Now, of course, the sum of all the delta xi's just recombines to give me the length of the entire interval, and I get b minus a and those cancel. So for any epsilon, we found a partition whose upper and lower sums are within epsilon of each other. Closed partition criterion is satisfied, therefore function is integrable. So a function is integrable if it's monotone or if it's continuous. But we also know that we can glue functions together. If a function is integrable on one interval and it's also integrable on the next, I can glue them together. So if a function has an interval where it's monotone, then an interval where it's continuous, then an interval where it's monotone, then an interval where it's monotone, I can glue them all together. Anything that is piecewise monotone or piecewise continuous, or piecewise combination of monotone or continuous, is integrable. So what does a function have to look like to not be integrable? So we already know of one example. The indicator function of the rationals is not integrable. And if you think about it, on any interval you look at, it's not monotone because it goes back and forth between 1 and 0, and it's not continuous because it goes back and forth between 1 and 0. Okay, so that would be a function that isn't even piecewise monotone or continuous. So if a function isn't integrable, it's got to be really ugly. You can't try to just draw something. If you try to draw something on the page, you're impulsively going to make something at least piecewise monotone or piecewise continuous, and those functions will be integrable. So it would have to be pretty terrible. So we have this theorem. A function is Riemann integrable if and only if the set of discontinuities is countable, meaning either finite or countably infinite. We're not going to prove this. It's just a little bit beyond the scope of what we want to get into, but it does basically establish which functions are integrable full stop. So a function is Riemann integrable, therefore Darboux integrable, therefore satisfying the closed partition criterion. These were all equivalent. If and only if the set of discontinuities is at most countably infinite. So the indicator function of the rationals, remember, was discontinuous everywhere. So on any interval, the set of discontinuities is the entire interval, which is an uncountable set. But anything you could try to cook up, if the set of discontinuities is countably infinite, it will be integrable. Okay, but we're not going to prove it, as I said. Yeah, it's a little too bad. It's not the worst proof in the world, it's just a bit beyond what we want to get into. Anyway, that closes off this video. Hopefully it wasn't too bad. It was a bit of a long one, but come on back and we're working our way towards the fundamental theorem of calculus, and that's exciting.